It's already 5. I guess we should start. People can join it too. So, hi everyone. Uh, Welcome to the week 12 live interactive session on the course Semiconductor Devices and Circuits, NPTEL NOC24 EE-143 tutorial. Uh, the course instructor is Professor Sanjeev Sambandhan from ISC Bangalore, and I'm the TA for this session. My name is Yavar, and the schedule that we followed throughout uh, the sessions was 5 p.m. to 7 p.m., right? Every Sunday, 5 p.m. to 7 p.m. And these were the contact details which you could have used to reach out to me, and you can still use to reach out to me. So, guidelines as usual. In case you have any query, you can raise your hand or you can ask in the chat window. Please ensure that your microphones are muted when you don't intend to speak. And I'll try to make it an interactive session. So I would appreciate your cooperation for the same. Uh, Please keep your pen and paper handy along with you, uh, including a calculator. The session recording link and the lecture notes will be shared by the NPTEL course team in the due course of time. And yeah, the prerequisites include the last week's lectures, which covered the following topics. Amorphous semiconductors were introduced, and uh, when we had a discussion on thin film transistors, right? You were taught this thing. So I'm assuming since there is no one at present in the meeting, I'm assuming you all would watch this session after attempting this assignment 12 first. Okay. So now let's move forward. So a brief recap. Introduction to amorphous semiconductors. So what are amorphous semiconductors? Could you write in the chat? There is one student in the meeting. So what are amorphous semiconductors and how do they differ from the crystalline counterparts? Okay, so amorphous uh, solid has a short range order, right? As you can see in this picture, this is amorphous one, right? Glassy solid on the left, and this is the lattice structure of the crystalline solid, right? This has got a long range order, and this has very short range order. Okay, and let me try it this way. So these have your short range order, right? Short range order. And then what about the melting point? Uh, how does their melting point differ from the crystalline counterpart? It turns out they do not have a sharp or characteristic melting point, right? Rather, they are softened in a range of temperature. Okay, so I'll write no sharp, no sharp melting point, right? Then they undergo irregular breakage, right? They do not undergo a regular breakage. On the other hand, this Breakage is irregular, right? Let me write that up. Undergo irregular breakage. And then the properties are direction independent, right? Or I should say isotropic. So the properties are direction independent. Okay. So it doesn't matter in which direction we are measuring a particular property. That property would be independent of the direction in which we are measuring. Okay. And then they are less rigid. Okay. These are less rigid. And then, yeah, examples would include fiberglass, you have your cellophane, right? Then there is Teflon, etc. I mean, I'm giving the examples for the amorphous solids. Okay. Then, I guess, let me not include examples in this PDF. Then we have thin film transistors, right? What about thin film transistors? How would you define them? How do they differ from our normal field effect transistor? Can you write that in the chat window? Sorry. Small thickness. Okay. So the thing is, I mean, I would say it's sort of okay answer. The a thin film transistor is actually a special type of your field effect transistors, where this transistor is made by thin film deposition, right? There is deposition of thin films of the materials, right? And your TFTs, they are grown on a supporting but non-conducting substrate such as glass. Okay, I guess I should write it as well. So your TFT, this is a special type of FETs where your transistor uh, is made by thin film deposition, right? And then, yeah, TFTs, they are grown on a supporting Okay. TFTs are grown on a supporting but non-conducting substrate, right? For example, your glass. Okay. And your TFTs, they differ from the conventional bulk MOSFETs, where the semiconductor material typically is the substrate. What is the substrate in the conventional bulk MOSFETs? Anyone? What is the substrate in our conventional MOSFETs? Please type in the chat. We're supposed to know this, right? I said that the thin film transistors, they are grown on a supporting substrate such as glass here. But what is the substrate in our conventional MOSFETs, bulk MOSFETs? It is silicon, right? I mean, the substrate is a silicon wafer, right? Okay. So coming to the application, what is the conventional application of TFTs? They are uh, used in LCD displays, right? Displays constitute one of the major applications of these thin film transistors. Okay, so I guess I should write the last point. So your application would be your displays, right? Matrix displays, etc. So with that, we'll start our first question. Okay, just a second. Just a second. Okay. So what is the value of the mobility of electrons in extended state in the amorphous material in the unit centimeter square per volt second? If your mu naught is 30 centimeter square per volt second, your this T free is 10 to the power minus 9 seconds. Your T trap is 10 to the power minus 6 seconds. What is the value of the mobility in extended state? Do you know the formula to compute that? Can help you with that. If your mu d is the mobility of electrons in the extended state in amorphous material, it is given by your T free divided by T free plus T trap times your mu naught, right? So this is the formula that you should use to compute it. Can you find it now? What would be the value of the mobility of electrons in the extended state in amorphous material? Please write the answer in the chat. I mean, this is just a plug the value problem, right? So this mu d would be 10 to the power minus 9 whole divided by 10 to the power minus 6 plus 10 to the power minus 9 into 30, right? And that would mean our mu d is equal to 10 to the power minus 9 whole divided by 10 to the power minus 6 into 30, right? This is 10 to the power minus 3 into 30, which is nothing but 0.03. What? Your centimeter square per volt second, correct? So that finishes this question. We'll move on to the next one. So when the operating voltage of your crystalline silicon MOSFET is compared to the amorphous silicon TFT, what is, I mean, the comparison sign? Is it greater than, less than, equal to? Which operating voltage is higher? Option A is correct, right? Your operating voltage of amorphous silicon MOSFET is higher than your operating voltage of your crystalline silicon MOSFET, right? So we'll move on to the next one. Now, you need to select all the states that contribute in the conduction mechanism in amorphous materials. Please answer this one. I'm assuming you would have already gone through uh, the last week's lectures, right? If someone is typing, extended energy states and the tail states. Yes, that is the correct answer. So as Prasad Rao answered. These two states contribute in the conduction mechanism uh, in amorphous materials. Okay, then we'll move on to the fifth question, which is following. So, which of the statements is or are true for your deep trap states? So, again, this could be, multiple options could be correct. So, which options do you think are correct with regards to deep trap states? Okay, so deep states exist in the mid trap. Yes, this is correct. Anything else? Deep states do exist in the mid band gap of the semiconductor. But is there any other option that is correct? Firstly, you can. What about this one, option A? Do deep states contribute to the conduction mechanism in amorphous semiconductor? No, right? So we can, I mean, discard this option, right? Then, do deep states exist near the valence and conduction band? No, right? Because we already said that these deep states, they exist in the mid band gap of the semiconductor. So there is no way this and this can be correct. So we are only left with one option, which could be correct, right? Let's study that. So do deep trap states distribution control the sub-threshold behavior of TFT? Do they control it? They do. Okay. So you may refer to the uh, lectures from the instructor for that. So it turns out deep trap states distribution do affect or control the subthreshold behavior of the thin film transistors. Okay, so we had two correct options for this question. Now we'll move on to the next question, right, which is question 6. So please attempt this one. I'll be waiting, right? And I expect an answer. I'll take a break, okay? Meanwhile, you can attempt this question. Okay, so Prasad Rao answered it as 25, which is the correct answer. So the answer is 25 centimeter per volt second. I'll still go through the solution once for others. So yeah, this is the correct answer. Let's go through the solution, which in fact is a simple one. So your mu d, right? Uh, which is the drift mobility of electrons. That is T free whole divided by T free plus T trap times mu naught. And mu naught is your this conduction band mobility, right? Or we can say free carrier mobility, right? And yeah, T free is equal to 20%, which is 0.2 seconds. And then your T trap is uh, see, your rest of the time in the trapped states, right? So T trap would be the remaining percentage would that would be 80%, right? And that amounts to 0.8 seconds, right? So I mean, I'm normalizing it. I mean, uh, even if you would consider, see, I took 20% of 1 second, right? And similarly 80% of 1 second. Even if you would have taken 20% of 2 seconds and similarly 80% of 2 seconds, that could have been factored out, right? Two and two would have been factored out and you would have been able to cancel that. I hope that's clear, right? So that's why I did the calculations for 1 second because that would make the calculations relatively easy. So this would be your mu d, right? Your mu d is 5 centimeter square per volt second. What is your mu naught? Your mu naught is something that we don't know, right? Then you can write 5 is equal to 0.2 whole divided by 0.2 plus 0.8 times your mu naught, which would mean your mu naught is equal to 5 whole divided by zero point 0.2, right? And that would be 25, right? So your mu naught is 25 centimeter square per volt second, right? Done. So which is the answer that was answered by Prasada. So now the next question. Okay, so this again could be a multiple. I mean, this could be a question in which multiple options could be correct. So which of the statements is or are true for the 3D density of states in the band gap? Would you answer it, Prasadra? Or should I tell you the answer? Okay, I'll tell you the answer. So, so is the DOS proportional to E minus EC raised for zero point 0.5 for amorphous semiconductor? No, this is not correct. Is the DOS proportional to exponential of E minus EC by KT for a crystalline semiconductor? No. For a crystalline semiconductor, that is not the case. There is no density of states for band gap for amorphous semiconductor. That is also not the case. And the last one is the option that is correct. We have exponential density of states in amorphous semiconductor, right? I mean, there are although various models. I mean, there are uh, three, I mean, density of states expressions that are known to me at least. One is the exponential density of states. The second one is the double exponential density of states, right? In double exponential density of states, there is one term corresponding to your deep trap states and the one term that is corresponding to your uh, tail trap energy states. Okay, and then there is a third model which is available in literature, which is Gaussian density of states, right? Because in fact, we can in fact show that the Gaussian behavior can be modeled by two exponential density of states, right? That is the reason why double exponential density of states and Gaussian uh, density of states are used for amorphous semiconductors. And to my knowledge, uh, mostly double exponential density of states is used for the amorphous semiconductors. Okay, so the most appropriate option in this case was the last one, that your DOS is proportional to exponential of E minus CC by KT for amorphous semiconductor. There is no way it would have depended up like this, right? There is no square root type dependency in case of amorphous semiconductor. Is that fine? Prasad Rao, is this okay? Okay. So we'll move on to the next one. So which of the statements is or are correct for the MOSFETs? What about the first option? Let's go one by one. Okay. So for amorphous semiconductors, the threshold voltage is defined by the gate potential when MOSFETs make a transition from inversion to strong inversion mode. Is this the correct option? Yes or no? Or if you don't know, just write, I don't know. Yes. So this option is in fact correct. So for amorphous semiconductors, our threshold voltage is defined by gate potential when MOSFETs make a transition from inversion to strong inversion mode. Okay. Now, what about the second option? For amorphous semiconductors, threshold voltage is defined by gate potential when Fermi level makes a transition from deep to tail states. Is this correct one? No, right? Why? Because, I mean, we already said this is the way the threshold voltage is defined, right? When MOSFETs make a transition from inversion to strong inversion mode, that is defined as the threshold voltage. The corresponding gate potential is defined as the threshold voltage. What about the second one? This is wrong, right? This is not correct. What about the third one now? Is third one correct or fourth one correct? Do amorphous semiconductor MOSFETs work in accumulation mode or do they work in strong inversion mode? would have been discussed in detail in the week lectures, right? They work in. Okay, you are typing. Both are not correct. No, I mean C is correct, right? I mean we do use amorphous semiconductor MOSFETs in accumulation mode. Okay, please go through the content again and I'm sure you will get it. So we do use them in accumulation mode. Fine. Just go through the lecture contents again. And if you are not sure why, then we can discuss it over a mail. Okay. So we do use amorphous semiconductor MOSFETs in the accumulation mode. Then we have the ninth one. So saying assume an N-type thin film transistor in which the trapped electron concentration is much higher than the electron concentration in the above threshold operating regime. Okay, so our trapped electron concentration is much higher than the electron concentration in the operating regime that is above the threshold. So the electrostatics, or I should say the Poisson's equation, is dominated by dash. Okay, so electrostatics Poisson's equation is dominated by dash and the drift transport under drain bias is dictated by dash. Okay, so your Poisson's equation is dominated by your trapped electrons. Okay, this option is correct. So our Poisson's equation uh, in such a transistor, right? In such a thin film transistor, in which your trapped electron concentration is much higher than your free electron concentration in your above, uh, I would say in inversion regime, right? Because above threshold operating regime is your inversion regime. So if that is the case, when trapped electron concentration is much higher, the Poisson's equation gets dominated by that, right? So uh, this one is trapped because your trapped electron concentration is the one that dominates. And while as for the drift transport, since the your trapped electrons are not free to move, right? So that is the reason in drift transport under drain bias, that is dictated by your free electrons because free electrons can move. Does that make sense? Is that okay? Okay. So that's why option B is correct. Then we'll move on to the 10th question, which is actually the last one, which I planned today because your actually this week 12 content was very short compared to other contents. That's why I mean this will finish up relatively faster compared to the other live sessions. So this is the last question. Uh, Consider a MOS capacitor with P-type silicon substrate. Okay, this is your conventional MOS capacitor. Okay, you have to consider this with a P-type silicon substrate at T equal to 300 Kelvin. It's doped to Na equal to 10 to the power 16 per centimeter cube. Okay, this is your Na, right? This Na, acceptor type doping, right? 10 to the power 16 per centimeter cube. And the oxide is silicon dioxide with a thickness of 55 nanometer. Okay, the area of the device is 2 times 10 to the power minus 3 per centimeter square. Sorry, centimeter square. That is the area. You need to assume the thermal voltage is 25.9 millivolts and your Ni is 1.5 into 10 to the power 10 per centimeter cube. Okay, so please compute the value of the total oxide capacitance of the device in picofarads. I'll pause and wait for you to answer. Okay, I'll wait for around 5 to 7 minutes because this would be the one after which we would end this session. We'll have a short discussion though after this question. So please stay in the meeting. I'll wait. Okay, please attempt this one. This is pretty straightforward. Okay, so we do have an answer, which is okay, 125. I guess you mean 126 picofarads. That is the correct answer. So I'll just we use this formula, right? C is equal to epsilon A by D, and which is epsilon OX, your epsilon naught A times your TOX. And this comes out to be as 126 picofarads. Okay, done. So you're saying please explain amorphous and TFT concepts in the next session if possible. Okay, I mean, I'll try to explain them briefly. How much long do you want them to be? Do one thing, mail me. Okay, just mail me how long would you want an explanation on amorphous and TFT uh, concepts in the next session, which will be our last session. Okay, the extra session will be last session for this series. Getting Monday session notification every week. Is it there? Link not opening. Okay, I guess you would see link would be the same. Link would be the same which you were using. Link, I mean, I have not changed the link. Uh, I'm not sure what would be the schedule for extra week. Have they let you know what is the schedule for the extra session? Could you just let me know in the chat? Is it on Monday? Six to eight Monday. I mean, mine session is my session scheduled from 6 to 8 on Monday? You mean the next date? Is it tomorrow? Wait, I'll check. Now even I am in doubt. Some other. Okay, okay, okay. Just a second. I'll confirm extra session if they have made it out. Just a second. Okay, I understood what you are saying. This the session that is scheduled on Monday. I'm not sure. The TA that is taking those sessions is probably not active, and I'm not sure if any of that is actually session three, right? You have three groups, right? Mine is group one, second group is taken by Ateeb, and third group is taken by someone from ISC, and this third one is probably not active. I'm not sure why. So that is probably the reason why you are not able to open that link. But the first two, my session and section, I mean, the two sections are active, mine and Adeep, so you can uh, watch anyone among them. Okay, and both, I guess the session two has already been taken by him, right? He would have already taken that session. His timing was from 3 to 5, if I'm not wrong, right? Yeah. So, okay, you will be, I mean, notified about the extra session timing in the due course of the time. And yeah, as you suggested, I would explain amorphous and TFT concepts as well in that extra session. And to those who are not present in the live session, if you want a particular topic to be discussed, please reach out to me via mail, preferably within 2 to 3 days, so that I could accordingly prepare for the extra live session. And we'll probably have a healthy discussion. And I expect probably all of you to join because that would be the last session, right? So with that, we can end this session if you have nothing to say. Should we end it then, Prasad? Okay, thank you. Bye bye.